Today I'm going to present some recent work that we've done, which is about improving quantum phase estimation. The paper is already up in arXiv, and the link is here, and also a QR code. To introduce this work, I'm going to start by talking about the wider problem that we care about, which is that oftentimes we'll have a physical system or about chemistry or materials, which is described by a Hamiltonian. And that Hamiltonian is going to determine what are the energy levels of that system. And we would like to know what those energy levels are. And we like to know that because it's very useful for many applications down the line. Chemists can predict how molecules bind and react and how materials behave based on knowing the values of these energies. Now, calculating these energies can be quite difficult, so perhaps you'd like to do that with a quantum computer. Now, there are two kind of distinct sub-problems here. One is, how do you generate the state on the quantum computer which describes the system that you care about? And the other problem is that, imagine you have already prepared that state on your quantum computer. How do you get the answer out? How do you read what is the value of the energy? So we're going to tackle this second problem about how do you calculate the numerical value of the energy with a quantum computer, given that you're already been able to encode your system and state onto it. So the main algorithm that we're talking about is called quantum phase estimation. And the setup is the following. So we have a state which has already been prepared. This could be, for instance, the ground state. It's going to be an eigenstate of the Hamiltonian. So this ket phi is the state that we've already prepared. And then we have a unitary operator u, which we know what it is. It's not the Hamiltonian, because the Hamiltonian isn't unitary, but it's going to be a unitary which encodes the Hamiltonian. So it's going to share the same eigenstates, and the eigenvalues of this operator are going to be related to the eigenvalues of the Hamiltonian. For a unitary operator, the eigenvalues are always complex numbers with unit modulus. So essentially, if you'd like to know what is the eigenvalue of this operator u, what you have to do is you have to figure out what is the phase in this equation. And once you have that phase, you can work your way back and understand what is the eigenvalue of the Hamiltonian for the state, and therefore what is the energy of the state you're interested in. So the task is essentially that we have this ket phi prepared on our quantum computer. We know what u is, and we'd like to find this phi, which is a number. And there's an algorithm for that. It's called the quantum phase estimation algorithm. And the most crucial thing to know about this algorithm is that it's not actually going to give you the answer. What it's going to give you is it's going to give you an estimate. So the real answer is going to be within some distance from that estimate. And the width of that interval in which you can guarantee that the answer will be is going to depend on how strictly you are going to allow errors. So we have a confidence level, which is typically something high, like 95%, 99%, something like that. And then corresponding to that confidence level, you'll have a confidence interval, which will say how large is the a span between your estimate and the answer for that given confidence level. So what is it that we want to improve? So our work is going to focus on three main goals. One is we would like that confidence interval to be as small as possible for any given confidence level. The second thing we want to do is we would like to have the quantum circuit which executes this algorithm to be as compact and small and not complex as possible. And lastly, we're interested in saving qubits. This is especially relevant for early fault-tolerant quantum computers where you might not have very many qubits available. So you would like to maybe use some techniques where you can use as few qubits as possible, but still have the advantages of having an accurate answer. So how are we going to do this? First of all, let's just look at what does quantum phase estimation look like. So this is a diagram from a textbook, which is showing you the steps that you need to do to perform quantum phase estimation. So I've numbered these 1, 2, 3, 4. And then you can see that the first step is to prepare a state on this extra register, which is called the control register. And the second step is to apply these powers of this operator U to the state that you've already prepared. Since it's an eigenstate, then applying U or powers of U does not change that state. However, this will induce a phase on this control register. And then finally, you do an inverse Fourier transform, and then you do a measurement. And then based on that measurement, you're going to read out the bits of your answer, and that's going to give you your estimate. So this is a very famous and known subroutine in quantum computing. And perhaps the most important thing to know about this is that the most expensive part here is applying these powers of U. And the reason why that's expensive is because in the context of a chemistry problem, this operator U is going to encode the Hamiltonian, which a power of U would correspond to essentially simulating the Hamiltonian evolution for a longer time, which means that there's not really any shortcut to doing a large power of U. So let's say you want to do U to the power of J, then essentially the best we can do is just do U J times consecutively. So as you can imagine, if we want a more and more precise answer, then we're going to have to make this control register larger and larger, which is going to increase the possible value of this index J. And if this index J gets very large, then doing this operation U to the power of J becomes very expensive. So yeah, that's where the expense comes from. And what we're going to do is we're going to modify each of these steps. We're going to get improvements on all of them and achieve our goals. So the first step, which was state preparation, the textbook tells you to apply a Hadamard gate to all the qubits in the control register. And what this does is it prepares a uniform superposition state. And you might ask, well, why do we do that? And the answer is that basically it's simple and it works well enough. That's what people would recommend you to do. But we know actually that it's not the best possible state you could prepare on that control register. In fact, by changing the state that you prepare on the control register and nothing else about the algorithm, you can decrease the width of that confidence interval. So you get a more reliable answer. So that was one of our goals. So we'd like to maybe choose a better state to prepare. And it's been known for a while that the best state to prepare on the control register is something called a DPSS state. These diagrams kind of show you what the state looks like. So a uniform state means that all basis states have an equal probability, whereas this DPSS state is going to have like a kind of a bump. And the way the DPSS state is defined is that it is the eigenstate of this operator here, which has the largest eigenvalue. Now, the trouble is that even though we know that this is a really good state to prepare, we don't really have a recipe for how to prepare it. Because like just looking at this definition, it's not obvious how you would construct the circuit which is going to prepare this. Now, there are techniques to prepare arbitrary states. You could just say, well, you know, it's just a list of numbers here, and we could have a a state preparation subroutine, which is going to, prepare any state we like, but that will come at a cost. And the trouble is that here in the textbook version, just applying a Hadamard to all of the control qubits is really, really cheap. But if you're going to do an arbitrary state preparation on this control register, then that becomes very expensive. And expensive in the sense that if you increase the size of the control register, then the cost is going to also increase exponentially. And that's not something we would like to do, because the size of the control register is going to actually determine how many bits of precision our final answer is going to have. So we would like to be able to scale that to be as big as possible. So we try to think what kind of other techniques could we use to prepare a state like this. And then we came up with this circuit here. This circuit here is actually a circuit used to prepare a matrix product state. And it's not obvious that a matrix product state is what we want, but you could take any state you like and try to approximate it with a matrix product state. And it's not obvious that this is a good state to approximate with a matrix product state, but that's what we tried. And it turns out that actually matrix product states give a very, very good approximation. Now, matrix product states have something called the bond dimension, which is essentially saying how big do these operators in the circuit get. And we found that bond dimension 4 is large enough to give a good approximation for this state, which in the context of the circuit simply means that these operators here will be at most on 3 qubits. So this is a 2-qubit operator, and then you'll have 3 qubits, and it will keep being 3 qubits, no matter how large the control register is. So, I mean, this circuit certainly is more expensive than the textbook version, but again, as a reminder, the most expensive part of quantum phase estimation were those control powers of U. So we have a budget to increase the cost of state preparation here a little bit. And the good thing about this matrix product state circuit is that if you add more qubits, then the cost grows linearly and not exponentially, because all you have to do is just add more of these 3-qubit operators, as opposed to doing some very complicated multi-qubit operators on like half the register or something. So before we kind of show you some evidence of this actually working, I'd like to point out that this circuit has a nice little structural feature, which is that as we are preparing this state, we're kind of doing it sequentially, qubit by qubit. We're doing this bottom qubit. Once we've done this first operation, we never really do anything to it later. So we can use that to our advantage to save qubits, and I'll show you how in just a moment. So to save qubits, we're going to use a little trick called the semi-classical Fourier transform. Now, the Fourier transform is this part at the end of the circuit, and there is a known quantum circuit for performing the inverse quantum Fourier transform. However, there is a variant of that, and that variant is called the semi-classical Fourier transform. And it achieves the same thing as the quantum Fourier transform that is recommended in a textbook, but what it will do differently is it will perform these measurements qubit by qubit. So instead of doing a transformation on the entire register and then measuring all of the qubits at once, instead, the semi-classical Fourier transform is going to do something to one of the qubits, measure out the result, and based on that measurement, it's going to do something to the next qubit, and so on. So it's going to kind of read out your answer bit by bit instead of all at once. And why this is useful is because it's compatible with our state preparation technique, which was also preparing the state qubit by qubit. So here's what we can do. We start preparing the state on the control register. So here's our operators. apply the first and the second and the third and so on. But since after applying the first, we're not doing anything more to this qubit later, then we can immediately start applying the rest of the quantum phase estimation circuit. We do the controlled power of U on the system state, and then we do the semi-classical Fourier transform, which prescribes basically doing a Hadamard and then a measurement, and then controlled on that classically, we're going to do a rotation on the next qubit. And the good thing about this is that once we've done this measurement here, this qubit is now free. What it means is that we can reassign it, we can recycle it. We can say that, okay, I've already done my measurement on this qubit, so now I'm going to just rename it, relabel it, and say that this new qubit that we're going to need here, this can just be the old one that we just measured out. So as you can see, like we can like kind of sequentially keep on measuring out the qubits before we've prepared the entire state on the control register. And this is really useful because then we don't need to have so many qubits at once. You can allocate only just 3 qubits to the control register for this purpose. You have these 3 qubits ready, and once you need a 4th qubit, you've already measured out the first one. So this is going to be really useful for an early fault-tolerant quantum computer where you don't have that many qubits to just spare. You would like to have a large control register to have a really accurate answer, but you just don't have that many qubits to allocate. So in this way, you can get away with just having 3 qubits and recycling them in this manner. Next, we're going to look at how well does this matrix product state approximation perform. And to measure that, we're going to look at the fidelity between the ideal state that theoretically is the best state against the state that we can prepare with that circuit that I showed earlier. So by measuring the fidelity, a fidelity of close to 1 means that these states are almost identical. And if the fidelity is 0, then that means that they're orthogonal to each other. Now, here in this table, I have written 1 minus the fidelity. So a very small number is a very good approximation. And here, as you can see, we have bond dimension 2 and bond dimension 4 for a variety of different parameters. This delta is the confidence level that you might want. So this delta equals 10 to the minus 2 corresponds to a 99% confidence level. And then this n is the number of qubits in the control register. And there's 2 things I'd like to point out here. One is that overall, these numbers are really, really small. So that means that the approximation is pretty good. So for bond dimension 2, you have fidelities that are just 10 to the minus 3 below unity. And for bond dimension 4, it's 10 to the minus 8. And I haven't even written bond dimension 8 or 16 or bigger ones here because they are essentially indistinguishable from the target state up to machine precision. But the way that we now should be picking which bond dimension to use is that we would like to use a bond dimension that is as small as possible because the cost of implementing that in a circuit is going to be smaller for a smaller bond dimension, but it has to have a good enough approximation quality that we would be happy to use it. So the kind of good compromise here is the bond dimension 4, where we have very, very high fidelities, and also it's quite cheap to implement. As I showed earlier, you never need anything more than a 3-qubit operator. So how does that actually translate into performance in quantum phase estimation? So this plot is going to show the performance for an 8-qubit example. This 8 is just picked kind of arbitrarily. It doesn't matter how many qubits you have in the control register, the behavior is going to look very similar. It's just going to be shifted. So this is a representative example. So here on this plot, this blue line is the uniform superposition state. This is what the textbook will tell you to do. And on the x-axis, you have the confidence level that you would like. Actually, 1 minus confidence level. So how to read this? So 10 to the minus 1, this means that at a 99% confidence level, you're going to get this kind of interval width for using the uniform superposition state, which here on this graph, it looks like it's 0.04. Now, but if you go to, this was 90%, but now if you go to 10 to the minus 2, which would be like 99%, which is something you'd more realistically want, then it doesn't even fit on the graph anymore, because the confidence interval width grows quite fast when using the uniform superposition state. Now, this orange line here, this is when you use the DPSS state. And the DPSS state is the optimal state, meaning that you can't do better than that. So this is why I've also shaded this area a little gray, which is indicating that there's no state you could pick which would give you a performance like that. The only way, well, you can still like get performance over here, but the way you would do it is you would have to increase the control register size. So for 8 qubits, this is the best you can do. And you see this orange line here, that's the optimal. And there's a little caveat here, which is that the DPSS state has like a parameter that you vary, in the sense that along this line, we are using different DPSS states, meaning that they have, if you remember earlier, I showed it was this kind of shape of a bump. What I'm saying is that for different confidence levels, you would slightly modify how wide or how narrow that bump is. So this is why, so that's how you kind of regulate it. And so now our goal is to see how well do our MPS approximations do compared to the ideal DPSS state. And the comparison that we do is the following. So if you just take the DPSS state, which was used to get this point on the graph, and you try to make an approximation of it with the matrix product state, and then you calculate again, based on that, what is the confidence level at that confidence interval for that state, then you will get the point here, which is like translated horizontally. Now, what we ought to see here is that for matrix product state of bond dimension 2, which is this green line, it's pretty much perfect up until like 10 to the minus 2.5. And then it really quickly becomes kind of bad. And then the bond dimension 4 is really good up to 10 to the minus 7, 10 to the minus 8 almost. And that is a really high confidence level. In any practical application, you probably don't even need that level of confidence for your estimate. Typically, what you would want is, 99, 99.9, and something around that. Maybe you even take, 4 nines, right? But in like any chemistry application, having a confidence level beyond 1 minus 10 to the minus 7 is, just not adding value anymore. So this is like further evidence that bond dimension 4 is a good choice, because it goes beyond what we really need, and it is kind of the cheapest option for doing that. There's also this dashed line, and the point of the dashed line is that these solid lines are obtained by directly, like trying to approximate this DPSS state. But obviously, if you try to approximate this DPSS state and you get a confidence level which is way worse than even something you had over here, then you would say, well, that's not a good result. I'm not going to use it. So in practice, you wouldn't actually try to approximate this DPSS state, because you would see that, oh, it's just not performing as I would like to. So therefore, you would pick a different MPS approximation and get like this dashed line, which is saying that this is the best matrix product state you could have for the control register, and the solid one is just like a direct attempt of trying to replicate this orange line. Then the last thing we'd like to improve about the circuit is we'd like to reduce the overall cost. And the way we would try to tackle that is we'd like to reduce the number of applications of this controlled U, which is to some power. The reason was that this is the most expensive part of the circuit. So this is how the textbook says you actually do it. You have your control state prepared, which they use Hadamard's, and then you just do these controlled powers of U. But in this scheme, one thing that you might notice is that if you add all these up, thinking how many applications of U you actually performed, then it's always going to add up to a power of 2. And this is just, because of the design of this circuit. But since we know that these controlled powers of U are pretty expensive, then, we would like to perhaps we'd like to use as few applications as possible. And currently we're limited to picking powers of 2. And it would be nice if we could be able to design a different kind of circuit where we still apply controlled powers of U, but the amount of applications of U that we perform is not necessarily a power of 2. If it can be any number, then that increases our number of options, allowing us to save up to 2 times the resources. So how can we do that? We can use something called unitary iteration. And so this psi here is the control state. And the unitary iteration, what it's going to do is, instead of just controlling on like separate qubits, it's going to kind of perform something like a for loop across this register. It's going to count from 0, 1, 2, 3, 4, and just keep counting, and on each count it's going to apply this U, and in the end you will achieve the same effect as this. But the advantage is that if you're, instead of applying consecutive powers of 2, which will all add up in the end to a power of 2, instead, if you're just counting, you can stop counting at any point. So that's nice. You can pick a dimension of the control state, which is not a power of 2, and you can apply exactly that many controlled applications of U. So this is a way to save the amount of U operations that we do. Now, there is still a kind of a question of, okay, even if we are counting to some number that's not a power of 2, we need to have a control state which would be compatible with that. So we would have to be able to also prepare the control state such that the dimension of the control state is not a power of 2. So how do we go about that? So we're going to use the following trick. These blue crosses here, this is just an example of preparing a DPSS state. So perhaps we want this curve here between the black dashed lines. This is representing a DPSS state which has a dimension of 34, which is not a power of 2. 32 and 64 are powers of 2, but 34 is not. So the way that we would do it is that we would take that DPSS state and we would extend it to further amplitudes so that we have a state that is a power of 2. So we'll have something which has 64 amplitudes. Then we can use the matrix product state preparation circuit, which we've been using, to now approximate this whole thing. Not just the part in the middle, but we're going to approximate the whole thing. And then, so if that is done also at with high precision, then we're going to have something close to this state prepared on our control register. And since the goal was to only have this part in the middle here, then we're going to do a trick where we apply this circuit up here, which is going to shift the state, and then it's going to set these values here to 0, which are beyond this dashed black line. And the way you can set these to 0 is through something called an inequality test. And the inequality test is a non-deterministic operation. It's going to, with some probability, it's going to give you exactly the state you want. And with some probability, it's going to give you some rubbish that you don't care about. And the way that you would do it is you just try it, and you have like a flag qubit which you measure. And if that qubit tells you that you were successful, then you keep it and you carry on. And if it tells you that you failed, then you just do the whole thing over again. And this is a viable approach because the success probability of this is actually very, very high. Typically, the success probability is going to be higher than the confidence level that you're aiming for. So this example here specifically is a DPSS state configured to achieve a 99% confidence level, and doing the inequality test to set these extra amplitudes to 0 actually has a success probability of 99.7%. So this is it's not deterministic, but it's like, good enough that you're not actually going to be worried about like failing to do this. So we've been able to, so now we have a way to prepare a DPSS state, which is not a dimension of 2. Then using that state, we can apply the unitary iteration that I showed earlier, so that we can apply U exactly as many times as is the dimension of the state. And the result is you do quantum phase estimation with fewer applications of this U operator. So how well does that perform? We're going to use a metric which is called relative increase in error. Essentially, we're going to look at how much worse does the matrix product state perform when compared to the ideal DPSS state. And the comparison that we do is that we just look at the relative increase in this delta. And the delta was, so 1 minus delta was the confidence level. So we've worked out a theoretical bound for this. We can show analytically that this relative increase is going to be smaller than this expression here, which is just using the target confidence level and the fidelity of our approximation. So we can already kind of predict that since we've kind of seen that we have a high fidelity approximation, then we're also going to have a low increase, relative increase in error. And something interesting about this bound here is that you see this term here. You can see that as the confidence level approaches the fidelity, then this term here blows up. And this kind of explains as well the results that I showed you earlier, where we saw that the matrix product states failed at some high confidence level. And the value of that confidence level at which they failed is probably not a coincidence, because this bound here also breaks down at precisely those levels. So if we just go back for a second, we can see here that the bond dimension 2 gives up at something like 10 to the minus 3, and bond dimension 4 gives up at something like 10 to the minus 8. And if we go to the fidelities, then these are also, for bond dimension 2, it's 10 to the minus 3, and for bond dimension 4, it's 10 to the minus 8. So this is just giving an explanation for why it's why this breakdown happens right at this point. It's because the fidelity is not high enough to guarantee any further performance beyond this. But this formula here, this is an analytic bound, but that doesn't mean it's a tight bound. So actually, the actual relative increase in error might be smaller than this value here. And In fact, it is. But we can directly just calculate what this is by comparing the states. So what we're interested in is that if we're using these control states, which have varying dimensions, it doesn't have to be a power of 2, then how well does the MPS approximation hold up? Does it depend on the dimension of the state? So here is the result. So on the x-axis, we have the dimension of the state that we are preparing on the control register. And on the y-axis, we have the relative increase in error. And then these different colored lines correspond to different confidence levels of the target DPSS state. So what we can see that for confidence levels of up to 99.99%, the relative increase in error is really negligible. So 10 to the minus 4, that's not an absolute increase in error probability. That's a relative increase in error probability. So this is like, very tiny, and you wouldn't be worried about that at all. So you'd happily use an MPS approximation that gives a relative increase, which is this small. And so overall, it's just like really, really low. But another feature that we see is that it has this kind of periodic pattern. And what the periodic pattern is showing you is that, well, first of all, the lowest values, the least error occurs at powers of 2. And the highest error occurs at just 1 dimension above a power of 2. And, then this gradually decreases until the next power of 2. And the reason why we have this behavior is that essentially the trick that we use to like extend the state and then like shift it and chop it off, it just seems that the matrix product state is like not as good as at approximating that extension as it is approximating the DPSS state on its own. So that kind of just explains that, okay, having more of those extra values decreases the quality of the approximation. But what we can see is that it's independent of the dimension in the sense that as you double the dimension, the relative increase in error stays the same. So whatever point you pick on this plot, if you double the dimension, which means you just move on the x-axis here, you'll reach the same relative increase in error. And that is that we argue in the paper that this is a feature of DPSS states. It's not a coincidence that this happens. And why this is valuable information is that at some point I stop kind of testing. I can't scale the dimension forever because my laptop gives up on these calculations. But what we can say based on this periodic pattern and also a theoretical kind of explanation that we give in the paper is that we expect this pattern to continue up until whatever number you like. So this is up to 24 qubits. So that means if your control state is like a 24-qubit DPSS state, then you're still having this great performance of the matrix product state approximation, which you can use, and that's already very good because that would mean that you can obtain an estimate for the phase that you're interested in with up to 24 bits of precision. So, or the hypothesis is that even if you want more bits of precision, we think that this pattern will continue, and therefore you can basically, there's no limitation on this technique for, in terms of how many qubits you're using. Now, let's talk about also more specifically about the implementation of this circuit. So earlier I showed you, you have just this circuit with these 3-qubit operators, but it was a bit abstract about what are those 3-qubit operators? How do we actually apply them. And we've worked out a way to decompose these 3-qubit operators into a bunch of single qubit rotations and C0 gates. So this is a very kind of practical diagram, which you can just use if you want to like implement quantum phase estimation. You can just use this, right? And these angles here, you can calculate what those angles should be based on, you know, the DPSS state that you're trying to prepare. You know, which confidence level is it for, and how many qubits are there in total, and so on. But this circuit that we have here, it's quite an efficient circuit, and it's efficient in many ways. It's not implementing an arbitrary 3-qubit operator. It's specifically implementing one of these guys. And what it means is it's taking advantage of two features. The first feature is that you have this incoming 0 state. If you know that one of the qubits is going to be in the state 0, then you can have a simplified operator, which would do something completely different on this. It would be in a completely different operator if it was applied to the 1 state. But since you know it's going to be a 0, you've kind of been promised that by the circuit, then you can get away with a simpler circuit. So it's taking advantage of that fact that we have a 0 coming in, and it's also taking advantage of the fact that the state that we're trying to prepare has real valued amplitudes. So the DPSS state is just the values of the amplitudes have only like real values. There's no complex phase, so that can make further simplifications. Now, this decomposition here is actually useful for not just preparing DPSS states, but this is just for matrix product states in general. In any other application where you're trying to prepare some kind of real amplitudes valued state, and you're trying to use a matrix product state approximation for it, you can go ahead and like use this kind of circuit for implementing these 3-qubit operators. In the paper, we also have kind of a more detailed derivation of how we constructed this circuit. And in principle, you can also like generate a circuit for a 4-qubit operator, 5-qubit operator, so on. So it's a useful technique. So now we could also want some numbers, right? How good is this circuit compared to other techniques that exist? So here, this equation, which I've numbered 29, is this is the amount of T gates that the circuit will use that I showed earlier. Now, the circuit I showed didn't have any T gates in it, but it had these rotation gates. And the assumption we're making is that the way you would implement a rotation gate is by synthesizing it using T gates. And T gates are kind of the metric of this is the most expensive kind of gate that you would be doing in a fault-tolerant quantum computer, because these are non-Clifford gates. Everything else are Clifford gates in that circuit. So we count T gates, but there's other works which count Toffoli gates. But it's still fine to compare those two to each other, because Toffoli gates, you can use Toffoli gates to prepare T states, and you can use T gates to kind of implement the Toffoli gate. So they're kind of interchangeable, and the way the trade-off works is that one Toffoli is equivalent to either 2 or 4 T gates, depending on which direction you're going in. And so which are the methods that we're comparing to? First, we compare against the Grover-Rudolph state preparation method, which is a way to prepare an arbitrary state. So that's if you're going down the route saying, well, I would like a DPSS state, but I'm not going to use the matrix product state approximation. I'm just going to exactly prepare the perfect state. But we're not going to take advantage of any structure of that. So then the best way of doing this is like described in various papers. And then the cost here, what we can see is this cost grows very rapidly with the number of qubits in the control register. So if you're trying to prepare a control state on 20 qubits or 30 qubits, the number of resources used are already noticeably larger than the other approaches. Here, by the way, this n is the number of qubits in the control register, and this log 2 1 over epsilon, it's essentially like a precision parameter. You can think of this number as the amount of bits of precision that you are using to approximate those rotation angles. So if I just go back here, you have these rotations here, and well, an angle can have any arbitrary value. It's a real valued number, right? But you have to make an approximation at some point and say, well, I only consider angles up to some number of digits. And then this is basically the number of digits. So this is a parameter to increase the accuracy of implementing rotations like that. So we compare it to arbitrary state preparation, but then we also compare it to a different technique to prepare matrix product states. So even if we agree that using a matrix product state is a good approach for preparing like an approximate DPSS state, then you can still ask, well, how would I do the MPS preparation circuit? And so we're using the circuit that we just showed earlier, but there's other approaches which use different kinds of circuits. So we kind of costed against those. And what we can see is that basically these values are quite similar. They scale similarly, but the main difference is that they're counting Toffolies and we're counting T-gates. So if you multiply this Toffoli number here by 2 or maybe by 4, then either way, we actually have a lower cost. So what we've kind of shown in this comparison is that compared to arbitrary state preparation, using a matrix product state to prepare a DPSS state is a very cost-effective technique. And secondly, if you're going to prepare the matrix product state, the circuit that we've shown in this paper is a really good way to do that, even compared to other state-of-the-art matrix product state preparation techniques. Additionally, something that our circuit has is that, or rather doesn't have, is that we don't use any ancilla qubits. This is just like a 3-qubit operator is just a bunch of operations on those 3 qubits. Whereas these techniques, these are actually making use of QROM, which is like quantum read-only memory. What they're doing with that is that for implementing rotations, instead of kind of classically computing what those rotations should be, instead what they're doing is they're using kind of a lookup table to coherently write the angle of rotation that they need into an additional register and then apply that rotation. And also they're going to be to do that, they also need to use some extra qubits for doing unitary iteration and other subroutines. So my point is that these other 2 approaches, in addition to having a higher gate count, they're also using extra qubits, which for like a big scale machine with like millions of qubits, you might not care that they're just using temporarily some extra qubits. But for a small early generation computer, where every qubit is kind of accounted for, then our approach also respects that and is able to do this preparation without involving extra qubit allocations. So what has this work basically concluded? We know that DPSS states provide the optimal confidence interval for phase estimation. That is a useful thing because then the answer you get out of your quantum computer is going to be as accurate as it can be. We've suggested a way to prepare these optimal states by making a slight approximation using a matrix product state. And we've just shown that matrix product states are actually really good for this task, and that a bond dimension 4 matrix product state in particular provides an excellent approximation such that if you're looking at confidence levels but smaller than something like 10 to the minus 7 below unity, then you won't be able to tell the difference in performance between a DPSS state and a matrix product state approximation. We've also shown how our technique can be adapted to various other techniques, which can help you either save qubits or reduce circuit complexity. So if the dimension of the state was a power of 2, then the circuit was quite simple. We had this sequential application of operators on each qubits, and we showed that if you combine that with a semi-classical Fourier transform, you're able to recycle qubits and have very few qubits used in the control register, even though the effective size of the control register can be as large as you like. And on the other hand, if maybe you're not that concerned about saving qubits, but you are very concerned about having fewer applications of U, then we showed how you can adapt this state preparation technique to produce a state which has a dimension that's not necessarily a power of 2. And then you can use that to just perform fewer controlled unitary operations, which were the most expensive part of the algorithm. So we have 2 distinct benefits which you can use in 2 different scenarios. Finally, we showed how do you actually implement the matrix product state that we've suggested. We have explicit circuits which are straightforward to use, and we compared the cost of those circuits to other known approaches, and we found that ours gave better performance. Now, for future work or for open questions, what remains is that in our work, we basically we observed that these matrix product states are very good, but we provided mostly numerical evidence. We didn't really manage to come up with an analytic proof which explains why you can always use a matrix product state for this task. We just tested it numerically, and it worked very well. So perhaps future work can explore a more fundamental kind of explanation of why this approach works and prove that it's going to work no matter what other things you change. And lastly, we showed these 2 benefits of saving qubits and reducing complexity, but currently it's a bit tricky to get both of them at once because the techniques that we use for saving the complexity, which were using the unitary iteration and also preparing that state with the inequality test, all these things, they kind of need access to all of the qubits in the control register. And that's something that's not really compatible with the way that we were saving qubits, which was sequentially kind of measuring out the qubits with semi-classical Fourier transform. So perhaps in future work, it's possible to find some bright ideas on how to maybe not combine these 2 things, but to find a different way of getting these benefits simultaneously. Yeah, and that's all. Thank you.